প্রান্ত শুনতে পাচ্ছ? প্রান্ত আচার্য শুনতে পাচ্ছ? ও মিউট করে রেখেছে। তোমারটা মিউট আছে? হ্যাঁ, এখন শুনতে পাচ্ছ?
স্যার ওই আমাদের ব্রডব্যান্ডের স্পিড স্যার মানে একদম কমিয়ে দিতেছে।
ও আচ্ছা আচ্ছা, ওকে ওকে
স্যার ওই
ওকে, তুমি যদ্দূর শোনো। Okay, there are another type of characterization in material science. This is the how the material behaves, or what are the properties of material. Say, for example, did this material have any fault? Say, for example, we have seen different types of defects. Say, for example, point defects, for example, dislocations, for example, striking fault, for example, grain boundaries. Did the material have any of this? Or if it has, what is its extent of fault? What is the extent of fault? So this is another type of characterization. Say, for example, you have prepared a nanomaterial. Is it a nano? Is the size of the material is of nano order? So this is a characterization. You have prepared a shell and core nanomaterial. So how can you prove that it is a shell and core nanomaterial? So you have to characterize that. So this is another kind of nanomaterial, another kind of characterization where we know what is the material, but we will see the condition of the material. That means, say, for example, we have to see the surface of the material. We have prepared a thin film. We have to see that whether this film is homogeneous throughout or not. Is there any pore? Is there any crack? Is there any boundaries? So this is another type of characterization. In material science, we'll see that type of characterization. We'll see that type of characterization. That means the faults or the beautifulness of that material. This is the characterization. So our next chapter is the characterization of materials. Characterization of materials, and in that chapter we mainly will discuss about the microscopy, because we can see the faults, we can see the surface, we can see the grain boundaries, we can see whether it is nanomaterial or not by the microscope. So we will see different type of microscopes here, and how it works. We'll see it. Now, before going to the chapters, we have to discuss about the microscopes. Now, we know about the microscope. We have seen the microscopes in our HSC laboratories, and we have seen the microscope in different laboratories also. Why microscope is used? Can you tell me? Can anybody tell me why microscope is used? What is the necessity of microscope? Can anybody tell me? What is the necessity of microscope? Why microscope is used? কেউ বলতে পারো কেন মাইক্রোস্কোপ ব্যবহার হয়? কেউ বলতে পারবে না মাইক্রোস্কোপ কি কাজে লাগে? আরে এমন একজন বলছে যার কাছ থেকে কথাই আসছে না।
স্যার যেসব জিনিস খালি চোখে দেখা যায় না ওগুলো
খালি চোখে দেখা যায় না তাকে ওগুলো কি করবে?
মানে ওগুলোকে দেখার জন্য একটু বড় করে দেখার জন্য।
That means you want to magnify a substance. Okay, we have a magnifying glass. Most of us have a magnifying glass in our biology dissection set. We have a magnifying glass to see the things magnified. This is one aspect. Another aspect is the resolving power. What does it mean? Let us go to the pen and paper. Okay, দেখা যাচ্ছে everybody? ঠিক আছে?
Yes, sir.
Okay, very good. So let us suppose here it is my eye. Here it is my eye, and this one is an object. This one is an object, and this is another object. This is another object. Both are same. You see here, both are same. But the distance from my eye, this object is closer to my eye, and this object is some distance to my eye. It is far away from my eye. So I shall see this thing, this object, what I call it, more what is the term? What will be the term? Bigger. This object bigger than this. Okay. Although both the object is same, the length of both the object is same, as because it is closer to my eye, it will look bigger than this object. It is correct. এটা বুঝতে পারছো না পারছো না? তুমি একটা জিনিস, দুইটা লোক একই দেশ, একই হাইটের, একজন একটু দূরে আছে, একজন একটু কাছে আছে, তাহলে তুমি দূরেরটাকে আর কাছেরটাকে সেম দেখবে না দূরেরটাকে ছোট দেখবে, কাছেরটাকে বড় দেখবে? কেউ কথা বলে না।
স্যার কাছেরটাকে বড় দেখা যাবে।
কাছেরটাকে বড় দেখা যাবে। So why? Now why? তুমি বলবে যেটা কাছে সেটা সেই জন্য। Not that. Because the angle, you see, you are making angle with I, this is the angle, say this is one angle, and this is another angle. So this angle is smaller than this angle. So you whether the object is bigger or it will smaller, it will depend on the angle of the object and in the eye of the object and the eye. So to see an object bigger or smaller, if you can change the angle, then you will see it bigger or you can see it smaller. If the angle, if you can change the angle, either in greater side or in a smaller side, you will see the object whether it is bigger or smaller, but although the size is same. So if you want a mosquito in a bigger size, what you have to do? You have to change the angle. If you can make the angle bigger, then you will find the mosquito, the size of the mosquito is large. Now, second thing is resolution. I'm telling about magnification here. Magnification. This is the magnification. So if this is more closer, you will see it more bigger. But if it is very close to us, if this is very close to us, you will not see him. You will not see him. So our eye has a limitation up to which we can see an object clearly. If it comes more closer, then you will see it more bigger. But here you will not see anything. It will blur. We'll see a blur object. If I place my hand closer to my eye, up to a certain distance, I shall see my eye, I see my hand very clearly. But after that distance, I shall not see my hand clearly. I shall see my hand as a blur. So magnification, if you magnify a substance more and more, it will not mean that you will see the object more and more bigger. No, not that. No, not that. After certain distance or after certain magnification, you will not able to see the object. It will looks like a blur. Now here comes the resolution. Why you will not see? Why you cannot see that when it comes more closer to you? Why you cannot see? Because what is resolution? Resolution is that you see this is a point and this is a point. You can distinguish between these two. Here there is a gap. But if it is like that, there is a small gap in between 2 points, but you cannot see it. That is called resolution. If you have a very sharp eye, if you have a very sharp eye, then you can see that there is a small gap in between the two points or two things. That is the resolution. So our eye cannot resolve the points when it comes very close to my eyes. That is the resolution. So magnification and resolution, these two things is very much important for a microscope. These two things is very much important for a microscope. We can we can we can we can we have mobile phone and the camera. We can see the zoom is about 10x, 5x, 6x. This is magnification. That means it is not x, it is 6 times or it is 10 times. You have a mobile phone, you have a camera, and you have zoom there. It is 6x or 10x. This is not x, it is 6 times or 10 times. It is the magnification. You can magnify an object 6 times from its original figure. But the resolution is different thing. The resolution is something about something related with your pixel or megapixel. You have a front camera of 36 megapixel. You have a back camera of 20 megapixel. You have 3 back cameras. You have 4 back cameras of this much of pixels. This is somehow related to resolutions. So as the pixel is increased, we will get the more and more clear picture. The more and more clear picture. Okay. Now, next thing, how can we magnify a substance? To magnify a substance, we require a lens. We require a lens, convex lens generally. Say for example, this is a lens. This is a lens, and it is its center. Now, this is the line passing through the center. This is the line passing through the center. And say, for example, this is an object. This is an object. This is an object. Now, a lens has a focus or focal point. Here it is the focal point. What is the focal point? The focal point is that if any light falls on that lens, it will bend down and goes to that point. This is called focal point. Say, for example, if this light falls on the lens and it bends down to this point. This is the focal point. This is the focal point. So all light will fall on the lens and goes with the focal point. Why it will bend? Why it will bend? Because of diffraction. Why diffraction occurs? Because of changing the medium. I told you in the very first lecture when we have seen the optical property of material. Then we have seen the diffraction when a light comes from a glass medium to the air medium, it diffracts. Now, if this light goes to the center, then if this light goes to the center, then it will not diffract, it will go as it is. It will go as it is. So this is the first line. It comes through this, and this is the line which comes through the center. It intersect with one another here, and you will find an image here. You will find an image here. It is called a real image. It is called a real image, and it is inverted. You are finding, you will find an image of this substance where here, and it is inverted. Now, if this substance, if this object, say for example, if I draw another lens, if I draw another lens, and it is the now it is the focal point, and say for example, my object is here. My object is here. So this is the another focal point. And if light falls here, it will go there. And you will find image here. Can you see the difference? What is the difference?
Yes, sir.
What's the difference? Sorry, it is the image is like that inverted. What is the difference?
The subject is magnified.
Magnified. Here you see the image, you see here the image and the subject, more or less same. But here you see the subject is here, the object is here, and you are getting the image, it is magnified. So if you place an object closer to the closer to your lens, you will get an image, you will see an image which is magnified. This is the main principle of a microscope. This is the main principle of a microscope, and of course it is an optical microscope. We call it optical microscope. Why optical microscope? Because light falls on that lens. from the object, light light falls on that lens, and this lens is known as objective lens. And this is the theory of a simple microscope. This is the theory of a simple microscope. Now, if I can draw another one. If I draw another lens here, and my drawing is not good. It is very bad actually. Not good is not bad. It is very bad. Now, this is the focus point. I have placed the focus point. I have placed the object before on the focal point. Now, if I place the object more closer here, what will happen? What will happen? You see, same thing. This two will not meet. If you see here, these two will not meet. Now, what will happen then if I extrapolate this line to this way and this line to this way? It will meet here. It will meet here. And you will get an image here. This image is known as virtual image. This image is known as virtual image, and you see the difference is that the real image is inverted, but the virtual image is not inverted. The virtual image is not inverted. So you can see an real image, or you can see a virtual image, depending on the position of the object with respect to your lens. You can see real image, or you can see the virtual image. So this is the theory of a microscope. This is the theory of a microscope. It is the magnification thing. You see, you are getting magnified. This is the image, this is the object, and this is the image. This is the object, and this is the image. You are getting magnified. So you can have a real image, or you can have a virtual image by your microscope. Now, there is another type of microscope which is known as compound microscope. It is somehow more complicated. It is more complicated. How it is? You see. This is a lens, and this is the plane, the lens. Say for example, this is the plane, and you have placed an object here. You can place an object here. Now, what will happen? This is the focal point. This is the focal point. So what will happen? Light will come from here, and it will will go through this way. Okay, and one more thing is going on this way, and you will find an image here. You'll find an image here. You know, it is nothing. But if you place another lens here, if you place another lens here, and if you see this, if you want to see this from this side, then what will happen? Light will fall on this. Say, for example, now this image will be the object of this lens. Here, this is the real object, and this is the objective lens. It forms an image. Now, this image, if we place another lens here, this image will be the object of this lens, and it will go this way. And say, for example, if this is the focus point, and it will go this way. So we'll get image here. Sorry, no, sorry, it will be like that. It will be like that. So you see, the real object is like that. We have magnified it to this portion. We have used two lenses, and this is the compound microscope. This is the theory of compound microscope. So here, this is it real or virtual? What it is? Real or virtual?
Virtual.
Virtual. It is virtual. Now it is?
It is also virtual.
Why?
So because it has the alternate direction of the object.
No.
Real.
It is real. When you find the object in the backside, then it will be virtual. If you find the image on the front side, then it will be real. So this will be real. This will be virtual. Whatever it may be, we got an image. We got an image, and you see it is more magnified than the single. Then you have if you have a single real image. So this is the theory of compound microscope. So if you increase the lens, increase the number of lenses rather, if you increase the number of lenses, you will find that your image is more and more magnified. But resolution is different thing. Resolution is the distance between two. The distance between two, whether we can identify it is two dots or it is a big dot. It is actually 2 dot, or it is actually a big dot. It is the resolution. It is the resolution. You are identifying it is to that 2 dots. Then you have a good eye. Good eye means you have an eye with good resolution. You have a microscope with good resolution. This is the. But if you increase if you magnify an object say for example 100 times or 1,000 times, but you cannot see it, that means you have a good magnification, but you do not have that much of resolution. So this resolution actually, the distance, generally it is about 6 into lambda. What is it is called? Say for example, a sine theta. Now, now what is lambda? Lambda is the wavelength. Lambda is the wavelength. A is the A is your the diffraction refractive index rather. Refractive index. And theta is the angle. Theta is that angle. Say for example, this much. This is the theta. Now, now, if you see that if this value is high, what will be the value of D? If this value is high, say for example, this is constant, this value is high, or say for example, if this value is high, theta value is high, then what will be the value of D? D will be small. Or if this value of lambda is small, so what will happen? The value is also small. If lambda is small, the value is also small. The whole value is small, so the value is small. So this resolution will be high when the value is small. This resolution will be high when the value is small. So so this is the fundamental things. Now we shall go to the main to our main chapter. These are the fundamental things. We shall go to our main chapter. Characterization of materials. Now, you see the resolution. We want to increase the resolution. If the resolution is high, we can see a magnified object more clearly. To increase this resolution, we have to decrease the wavelength. If the lambda value is small, then the resolution will be higher. Then the resolution will be high. But in case of light, we have a limit. Say, for example, in a visible light, in the visible light, we have a lambda value, that means wavelength value, there is a limit. So we cannot prepare a microscope with a much higher resolution. Say, for example, we can prepare a microscope up to 1000x or 2000x up. That means it can magnify 1000 times or 2000 times. Actually, it can magnify more, but we cannot see that magnified object because because of resolution. So, uh, uh, we have a limitation to see an object more bigger because of its resolution. If we use light, so so the scientists wanted to go beyond it, and they have invented electron microscopy. Why? Why electron microscopy? Because the wavelength of electron is as small as about zero point 0.2 nanometer, whereas the wavelength of light is about 250 or 300 nanometer. So the lambda value, it was, or it is, for light is 250 nanometer, but for electron it is zero point 0.2 nanometer. So I can get a higher magnification, much higher magnification, with a very good resolution. So electron microscope are scientific instruments that are used a beam of energetic electrons to examine object in a very fine scale, without using light, without using photons. We are using electrons. Why electron microscopes are developed? It is due to the limitations of light microscopes, which are limited by the physics of light. We have we have a we have a definite wavelength of light. We cannot go beyond that wavelength. It is about, say, for example, 250 to 300 nanometer. We cannot go beyond that 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 wavelength. But if if we use electron, we can go beyond that. In the early 1930s, this theoretical limit had been reached, and the scientific desire to see the fine details of the interior structure of organic cells. That means if you want to see the nucleus of a cell, you cannot have it. You cannot see it by the light microscopy or optical microscopy, because this required 10,000x plus magnification, whereas you can have at most 3,000x magnification in the light microscopy. So scientists invented the electron microscope. The first electron microscope invented is the transmission electron microscope, and then subsequently scanning electron microscope is invented. Is invented by this scientist von Arden, and the transmission electron microscope is developed by Max Knoll and Ernest Ruska in Germany in 1931, and the scattering electron microscope is developed in 1938. If you see the if you see through an optical microscope and scanning electron microscope, the surface of substance, you will see it like that by optical microscope, and by scanning electron microscope, you see the surface is like that. You can see more clearly, and the resolution is very high. You see here, you see here, the resolution, you see the surface more clearly. You see here, you have a crack on that surface here. You cannot see it here. You cannot see it here, but you have seen a crack here. So this is actually difference between optical microscopy and electron microscopy. Now, scanning electron microscopy. So what is an scanning electron microscopy? What is the main theory? Actually, in the scanning electron microscopy, you see here, from here, a beam of electron pass through a set of lenses, and an scanning coil. This is also lens. Actually, here this is one lens and this is another lens, and the electrons are allowed to fall on the specimen. This is the specimen. The electrons are allowed to fall on the specimen, and the interaction between the specimen and the electron is measured by some detectors. The interaction of electrons and the specimen is measured by some detector, and from that interaction, from that measured interaction, we can tell about the surface of an object. So in scanning electron microscope, what we do, what we can scan the surface of an object by an electron beam, so that we can tell about the morphology and different thing of that surface. Say, for example, your eyes are closed, and I have given you a stone on your hand, and I am asking you how is this stone? So you can tell me, sir, it is rough. One side it is smooth, another side it is rough. We have a bump on this stone. How you can telling it? Your eyes are closed. You are scanning it by your fingers. You are scanning the stone by your fingers, and you feel whatever the stone is like, and you can tell me. This is the scanning. I cannot see by scanning electron microscope the object. I can see the object by scanning electron microscope. But by scanning this, electron will give many information, and from that information we can conclude about the surface of the object. So what what type of information we can get by SEM? We can get by SEM the topography. What is the surface features? That means how it looks, its texture, relation between this feature and material properties. What is the texture of that substance? Its morphology. the shape and size of the particles making up the object. That means you have an object, and some molecules or something is made the object. So you can tell, SCM can tell what will be the shape, what is the shape, and what is the size of the material, that of the particle that makes the object. Composition, you can tell the composition of the material, whether it is made of gold, or it is made of silver, or say for example an ornament. You have an ornament, and it is made of gold and different types of other metals. So so you can tell the composition of the ornament by means of SCM. And you can also sometimes, not always, get the crystallographic information by SCM, scanning electron microscope. Now let's see the details about the scanning electron microscope. First, what are the advantages? You see, the magnification is in the optical microscope is from 4x to 1400x. But in SCM, the magnification is 10x to 500 kilox. Not 500x, 500 kilox, 500 into 1000x. So you can magnify that much. You see, the resolution is 0.2 millimeters. What does it mean? If you place two substances at the distance 0.2 millimeter, an optical microscope can differentiate the two. If this substance is the distance of these two substances is below 0.2 millimeter, say for example, it is 0.1 millimeter, the distance between two is 0.1 millimeter, then the optical microscope cannot differentiate that there are two substances. It will tell that there is one substance. But here you see in SCM, the resolution you can get 1.5 nanometer. You see, if these two substances is distanced to 1.5 nanometer, then the SCM will tell that there is two substances. This is in millimeter level, and this is in nanometer level. So it has a very high magnification, as well as high resolution also. So we told you when we have shown you the figure, if the D value is small, then the resolution is high. This is the D value. Now, electron solid interactions. I have told you that we shall pass the electron through some lenses, and the electron will hit the object, the sample. Say this is the sample, the blue one, this is the sample. So this sample is made of different types of atoms. It may be say for example biological sample. It may be your chemical sample, whatever it may be. It will have different types of atoms and molecules in that sample. Now, when electron beam hits on that sample, there are a number of incidents can occur. First thing, you can find some secondary electron going out from that sample. What does it mean? That the sample contains different types of atoms, and this incident electron hits on the electron of the sample, on the electrons of the sample. The sample, say for example, this is a gold sample. So the electron will hit on the electrons of gold, and if the energy is greater than ionization potential, then the electron will go out from the gold atom, and you will get the secondary electron. So what is the secondary electron? If an electron hits on an atom, and if it hits on the electron, then the electron will go out from that atom, and that electron is known as secondary electron. So you will get many secondary electrons from the sample. This one. Second thing, you will get backscattered electron. This electron will hit in the sample, and some of the incident electron will hit on the nucleus of the atom. When it will hit, you can imagine about Rutherford's atom model, and instead of alpha ray, you can bomb an amount of electron, and some of the electron will hit on the nucleus. So the electrons, if the electron hits on the nucleus, it will bounce back. This is called elastic collision. If the electron hit on the nucleus, the electron will be bounced back, and you'll get backscattered electron. This type of electron is known as backscattered electron. Now, there are another type of electron that is called agar electron. You will know what is agar electron. If the incident electron beam hits the inner shell electron, not the outermost orbit electron. If the electron hits the inner shell electron, then what will happen? The inner shell electron will go out. That is called agar electron, and electron from the outer shell will come to the inner electron, and X-ray will produce. That is called X-rays. So you see agar electron, and you'll find X-rays also. Some electron will go out, and it will scattered. It may be elastically scattered. It may be inelastically scattered, or it may be unscattered electrons. So there are a number of incidents happen when an electron strikes on the sample, but we require only 2 or 3. We require the secondary electron, we require the backscattered electron, and we require the X-rays. Not our electron, we require the X-rays. Why we require that, I'll tell you later. So this is the electron solid interactions. Now, what is the scanning electron microscope? Now, at first, number one, the virtual source at the top represent the electron gun producing a stream of monochromatic electrons. What is that? You require electron as because it is electron microscope. So you require electron. If it is optical microscope, you will require light. Without light, optical microscope will not occur, or optical microscope will not function. It cannot function, or an optical microscope cannot function in dark. So electron microscope, for electron microscope, you require an electron, and a beam of electron will strike to the strike your sample, and different incidences will occur, and from that incidences we can conclude that this will be this type of substance. Now first you have to find out the electrons. You require electron. From where you require electron? uh, it is an instrument called electron gun. Electron gun produces electrons. How it produces electron? It has an tungsten filament. The electron gun, there are 2 or 3 different types of electron guns. The first one is the most simple one. The electron gun has a tungsten filament. If you pass electricity to that tungsten filament, if the voltage is high, then the tungsten filament will produce electron. The tungsten filament will produce electron, and this electron we shall use to measure the to hit to the object. Now there are another type of source of electron, which is known as field emission electron. A very sharp tip of metal. If you place your voltage, or if you place what is that called electric field. If you place electric field to that sharp pointed metal, then from that pointed metal, electron comes out, and this is the source of electron. So there are 2 types of source. One is tungsten filament, or different types of filaments, and another is field emission. So by any way, you will get the electron first. So this is the first you have to first you have a source of electrons. Next, you will find a condenser lens. First condenser lens. There are another condenser lenses. The first condenser lens. What is the requirement of this lens? This is actually an anode, a positively charged substance, a positively charged lens. What is the use of this lens? From here electron will come, and this positively charged lens pulls this electron towards this way. This positively charged electron pulls this electron. It is scattered. The electrons are scattered. Now this lens pulls these electrons toward this way, and this is an aperture. The electrons goes through this way to a second condenser lenses. The stream means the stream of electron is condensed by the first condenser lenses. This lens is used to both form the beam and limit the amount of current of the beam. So what it does, it forms a beam of electron. It is scattered when it is produced. This lens what it does, it forms the beam, and how much electron the beam will contain, it will also limit that, and it will pass this through this aperture. Now, you see, this is the condenser aperture. Number 3, the beam is then constricted by the condenser aperture, eliminating some high angle electrons. Eliminating some high angle electron, that means the electrons are scattered. This aperture eliminates that electron that are scattered. Now, the second condenser lens forms the electrons into a thin, tight, coherent beam and is usually controlled by a fine probe current knob. This is the second condenser lens. It forms what it does. What is the requirement of this lens? It forms this beam to a. You see, this is first, and this is second. You see, this is more thinner and tight your beam, and it goes to the objective aperture and through a scan coil. This is known as scan coil. What scan coils does, it scans, it can scan, it can bend, You see, this is the sample. Here electron beam strikes, and if you want that the electron beam will strike here, if you want the electron beam to strike here, then this scan coil bend the electron beam towards here. This scan coil actually scans this electron beam by reflecting the electron beam, bends this electron beam towards here, A set of coils then scan or sweep the beam in a grid fashion. Grid fashion means, you know what is grid. So it comes this way, then this way, then this way, then this way. This is the grid fashion. So these coils are actually responsible for scanning the sample. The final lens, this is the final objective lens. This is the final lens. The final lens objective focuses the scanning beam onto the part of the specimen desired. It bends the electron beam, and this lens strikes to the to the specific point. And before the beam moves to the next dual point, these instruments count the number of interaction and display in the pixel. So, so what will happen then? From here, your secondary electron comes out, and a detector is here. It detects the secondary electron. From here, backscattered electron comes out, and the backscattered electron is detected by backscatter detector. If from here X-rays come out, then the X-rays will be detected by X-ray detector. So there are different types of detector here, and that will detect the changes of the sample. So this is an actual SCM instrument. Here is the column by through which an electron beam goes here, and this is the sample. This is the sample chamber where you can insert the sample to the column, and these are the lenses objective aperture I have shown you here. So electron, this is the summary. electron source to produce electron, magnetic lenses to magnify the beam, magnetic coils to control the modify the beam, apertures to define the beam, prevent electron spray, etc. It should be the full column. This full column should be highly vacuum. Otherwise, if there are some gases inside this, the electron beam will strike with that gases, and you will not find any energy that will strike to the sample. So, a vacuum system must require on that scanning electron microscope. And third section is signal detector and display. The detector, the detectors I told you, the background, backscattered electron detectors, the secondary electron detectors, they are connected with a display, and they will give the image on the display. There are some ways to prepare the sample of SEM. Actually, the column should be high vacuum. So you cannot place any sample which is say, for example, which have water. Say, for example, you want to see a alive your cell. In an alive cell, there are about 90% of water. So you cannot place it there, because water molecule will go through the tunnel, and which will interact with electron, and the whole system will be destroyed. So you cannot use a sample which can evaporate, Now, sometimes coating is required. Because this coating will allow the electron to fall on the sample. Generally, gold coating or different types of coatings will be there. So coating is there. Sometimes you use carbon tape or carbon paint on that sample. It is actually depend on the type of sample, which type of sample you are using. This is the scanning electron microscope, and we'll see transmission electron microscope tomorrow.